by the perfect squares. So what type of series is that one on the right technically? It is a p-series. So like if I wanted to write a generic formula for it, like we know this is going to be equal to the series of 1 over n squared, because it's basically all of your perfect squares in the denominator. And we're starting with 1/4, so I'm basically starting when n is equal to 4 and going up to infinity. Not 4, 2 squared, which is 4, and then infinity. Try that again. N is equal to 2. Most important part there is that we're comparing it like 1 over n squared, which is a p-series test. So let's just go ahead and like justify it. What do I know about that p-series test? Like p would be equal to 2. Why is that important? That's greater than 1. If p is greater than 1, what do we know about that series? It converges. So series converges. How do we know? By the p-series test. And the idea behind a direct comparison test is if we know something about this series, which we do, we just proved that it's convergent, and if we know one that is similar to it, we can sometimes, but not always, draw a conclusion. How is this second one similar to that p-series? Looking at those denominators, if you were to try to write a series for it, I still see it's 1. How are each of those terms individually comparing to the denominator that we see of the known one? 1 more, right? So if I want to write a formula for it, instead of just 1 over n squared, it would be n squared plus 1. Starting point is not as important, again, for these, but it would start, again, at n is equal to 2 to infinity. So the idea behind a comparison test is we want to see how they compare and then see if we can determine that the one we're comparing it to would also converge or also diverge. And how do we do that is we are going to basically compare the terms. And what do I mean by comparing the terms? This one that we don't know anything about, all of its terms is always 1 over n squared plus 1. The one that we know something about, its terms are always 1 over n squared. We know that this series is going to converge. That is a fact. We have proved it. It converges by the p-series test. And when I say compare them, you want to figure out if the unknown series is always going to be like inside of the known or outside the known. And what do I mean by that? Is it going to be bigger or larger than the one that we know about? So how do we think about that? This 1 over n squared plus 1, it has the bigger denominator than 1 over n squared. But when your denominator is bigger, is your number overall going to be smaller or larger? Smaller. So I know that this expression is always going to be less than that expression. Some students like plugging in numbers just to test that first. You can. Just don't like plug in like 0, but plug in like 1, 2, and 3. And you will see that 1 over n squared plus 1 is always smaller than 1 over n squared. And then the idea behind a direct comparison test, well, if 1 over n squared is converging, what do you think we can say about anything smaller than 1 over n squared? It also converges. So how we would form that? So the original series also converges. And the reason we're using for this one is going to be DCT, the direct comparison test, because we are directly comparing one series to an easier. And that's going to be the basic kind of gist of how we're using the direct comparison test. It's honestly one of the ones that I personally, not that I just sit around and prove convergence all day long, but when I'm working problems like this, it is one of the kind of go-to ones I jump to if I don't have an easy geometric series or p-series. In fact, I typically would do this one over the integral test any day because I don't have to find an integral, I just have to compare it to something that I know. So let's try another one. And let's look at this one. So I have one series that we should be able to prove pretty easily, one that we can't prove so easily. They are related, and we'll basically be able to kind of draw some conclusions based on the relationship. Which one do we technically already know something about, the one on the left or the one on the right? The one on the right, because what type of series is the one on the right? It's another p-series. It is the p-series for n to what power? N to the 1/2. That's the series I'm comparing it to. When you are doing a direct comparison test, I will say you don't have to identify like the starting value. As long as you identify the formula for the series, that's fine. We are going to have to still justify it, so I'm going to have p is equal to 1/2, which is less than 1, so the series is going to do what? Diverge by the p-series test. So we have proved the simpler one diverges, and now we want to see if we can draw conclusions about that of the one that we're trying to find. How do we do that? We want to be able to compare terms. The terms of this one is basically 1 over n to the 1/2. If you're to write a formula for the terms of the one we're trying to find, what formula would you use? 1 over n to the 1/2 minus 1. Like we can kind of see that in the arrangement of it. We know that this one diverges. We have proved it. We want to see how this one related to it compares. Well, 1 over n to the 1/2 minus 1, is that going to be bigger or smaller than just 1 over n to the 1/2? Bigger. And again, my reasoning, again, you plug in values, you think by subtracting 1, you make the denominator smaller. If the denominator gets smaller, then that overall number is going to get bigger. So we know that this is true. And then we can draw a conclusion. Well, if 1 over n to the 1/2 diverges, like it is so big that it's going to diverge, what do we know about anything bigger than something that's already diverging? It also diverges. So series also diverges by the direct comparison test. So that's basically the idea that we're looking at for the direct comparison test. I will say what some students have trouble with. I gave us 2 series. Most of the time, you're just going to have 1 series, and you'll have to come up with the one that's similar to it, which we'll, of course, look at examples like that. Let's go ahead and formalize it, though. The direct comparison test. Main idea of it is we are going to compare the series to a simpler series. What will that simpler series be? It will often be a p-series, or it will be a geometric one. Those are the ones that we pretty much know automatically. So that's going to be the one that you're going to want to draw comparisons with. And then basically there's going to be 4 things that can happen. We've seen 2 of them already, and then the other 2 are going to be not as exciting. The first one we have is the one that is given is contained within a convergent simple series. Another case that can happen, the one that is given is bigger than a convergent simple series. Or the one that is given is less than a divergent simple series. Or the one given is less than a divergent simple series. I am going to add some things that aren't as important, but I do want to give like technical stuff. Technically, this first one, it can be less than or equal to. Like if it's equal to, then it is the simple series, and it is always going to be greater than or equal to 0. And yeah, that's the only thing I would really want to add. Yes.
I think 2 of your signs are the same.
2 of my signs are the same. I should flip this last one. Thanks. There we go. And again, I think of this like pretty logically. Like I don't by any means memorize this. Like I think it's pretty easy if you think about it. So if the one you're trying to find is smaller than one that already converges, what do you know about the one you're trying to find? It also is going to converge. Again, that's why I'm like, don't memorize these, just kind of think through it logically. What about if the one you're trying to find is bigger than one that converges? Can we say a statement with certainty of what it's going to do? No, it could still converge, or it could end up diverging. So it's going to be kind of the case of like no info, we're going to have to try something else. What about if your given one is smaller than one that diverges? no info again. So like it could diverge, it could still be big enough and diverging, or it could be small enough that it's going to converge, so we would have no info as well. And then this last one is the one that we saw. If your given is bigger than one that's diverging, then we know that it's also going to have to diverge. The two that are no info, I'm going to go ahead and tell you so you can fill it in, but that's where the other comparison test is going to come into play, and it's called the limit comparison test. So there are cases where the direct comparison test won't work, and those are the two cases where it wouldn't work, but again, there are two cases where it definitely can work. Questions on the basic idea of the direct comparison test? All right, let's look at, I have 3 examples to look at. And I'm going to skip that one. And this is what I'm doing. So I have used the direct comparison test to determine whether each series converges or diverges, or if its convergence can't be determined by this test. So I have 3 here, like you can probably guess that some of these converge, some diverge, and some will be no info. And the first part when it comes to the convergence test is kind of like, let's talk about when we want to do a comparison test. Looking at this first one, this is the series of 2 to the n over 5 to the n plus 3. It's not a known one. It's definitely one that I wouldn't want to do the integral test for. That's not going to be an integral that is pretty easy to find at all. But we can use a comparison test. Why would I want to use a comparison test? I look at this and you're like, man, I really wish this looked like another test. And you kind of think about like what test it looks similar to. Looking at that first one, what does it look most similar to? A geometric. And typically when you're trying to decide, these aren't limits, so I don't want to use the phrase what matters most, but these are series going out to infinity, so you can think of it in some ways like that. So you do always have to write down the series you're comparing it to. So I'm going to go ahead and do my sigma notation. And the series I'm comparing it to is going to be 2n over 5n. That is the series that is directly related to that one that we were given. Now, after I've written that, I am going to go ahead and simplify it so I can kind of identify it correctly. If I want to show this more obvious as a geometric one, that's just going to be 2/5 to the n. But I do need to show again, and I'll go when we finish it, kind of highlight the minimums that we would have to write down. And so now I want to justify the simpler one. You have to take the time to justify the simpler one. So I look at this simple one. The absolute value of r is equal to 2/5. Why is that important? It is less than 1. So what do we know about that series? It is going to converge by the geometric series test. That's going to be step 1. Identify the simple series, then justify the simple series. Second step is you want to compare the terms. So I have the one that was given, and I want to compare it to the one that we are using as the simpler one. I could compare it to 2/5 to the nth power, but your comparisons are going to be a whole lot easier if you use that original way that you rewrote it. Because if you use that original one, pretty much everything's the same, but in that one we're trying to find, we're adding 3 in the denominator. So the denominator got bigger. If your denominator got bigger, what is that number overall? Smaller. So this one is always contained within that one. If the simple one converges, what do we know about anything smaller than it? It also converges. So we can have, so the original series also converges, but by the direct comparison test. The only thing that you're looking at right now that would be considered optional is where you rewrote it as 2/5 to the n. Everything else would have to be there. You would still need to identify that the r is 2/5. You wouldn't have to rewrite it to identify it, but you would need to clearly state the series. I know in the AP exam, a place where students often lose points is they'll just write like 2n over 5n, but you definitely want to make sure you show clearly that you are comparing it to a series. Notice I didn't have to put like n equals a number and infinity on it. As long as I put that sigma sign, it's clear that I am comparing this to a series. Go ahead and try the bottom two for me. And again, the first step is to identify a simpler series that's related to it. And then see if you can justify your answer appropriately. So justify the simple one, and then compare the terms. Also be careful if it does give you like no info. But go ahead and try those two for me. I've written out the simpler series. I haven't finished either of those, of course, but you can kind of check at least the first statement for each of them. So again, the first step, let's kind of talk about again, because we do have a lot of tests we've learned and a lot of tests that we still have to learn. Looking at this first one that you see right now, why does it make sense to use a direct comparison test? Like when I see that problem, I see n raised to a power, so that screams out to me like, hey, this really badly wants to be like a p-series. It's going to be related to a p-series. So I want to find a p-series that I can compare it to. So what series is it directly related to? It's going to be directly related to the series where I just take off that -6. And that is required for you to show. Again, you want to show that series. What's optional, and again, I always write it down just make sure I identify my values correctly. Simplifying that series, we do get 1 over to n to the 2/3. So p is equal to 2/3, which is less than 1, so we know this is going to diverge by the p-series test. And then I do want to go ahead and compare the terms. In the one that we're trying to find, we are subtracting by 6, so the denominator is getting smaller, so the overall number is always going to be bigger. So the thinking is that simple series diverges, so what do we know about anything bigger than something that's already diverging? It's also going to diverge. So we can have, so series diverges by the direct comparison test. Questions on that one?
When we put a direct comparison test, we don't have to also put like p-series test.
No, you only need to write it once. So, and it's because we justified the first one by p-series.
Oh, okay, yeah.
This one we couldn't use a p-series because it's not technically a p-series.
Yeah.
So you wouldn't need to rewrite it, no. Then look at that second one. I think this one is just a little bit trickier when you get to the comparison part. What's the simple series? Again, always write that down. That's going to be the 5n over n cubed. I simplify that just because I do want to go ahead and see an easier one. Also a p-series. When you're doing the direct comparison test, it's probably going to be a p-series or a geometric one. P is equal to 2, which is bigger than 1. So that is going to converge by the p-series test. So let's compare the terms. I have 5n plus 4 over n cubed minus 4n, and I'm comparing that to 5n over n cubed. Which one is going to be the bigger one? The one on the left. You can do this without plugging things in. The way I think about it is these are series that going out, like n is increasingly getting large. In that denominator, you're subtracting minus 4n, so you're going to end up being like subtracting a really, really large number compared to that numerator where you're just adding a 4. So that denominator is going to be getting kind of like smaller in some regards. Or some students just feel safer and they just like pick a number they like, 2, plug it in for n and see which side is the bigger one and which one is the smaller one. That will hold true.
2 doesn't,
Say it again.
I don't think 2 works for this.
It starts at n equals 3. So yeah, choose something bigger than 3 and then it will work. Thank you. So then what conclusion can we draw from this one?
No.
Nothing. So like if the smaller one is convergent, that bigger one, and again, why we don't know, it could be so big that it diverges, or it could just be fairly bigger and still end up converging. So I would say something like, so the direct comparison test gives no info. So what do we do when the direct comparison test gives no info? So like we could try to do like an integral test. I can look at that one and that just doesn't look like a fun integral to find. I would probably have to start off by doing like partial fractions on it. We don't want to do that. So we want to have like an easier test that can also work. It is still going to be a comparison test. And by its name, you can probably assume that it is going to involve some limits. Questions on the DCT before we go to the LCT? Yes, Alex?
For that last one, could you also use the nth term test?
The nth term test, well, okay, so yes, the limit of that one goes to 0. So the nth term test gives no info. So you try something else. So you basically, whenever you get no info, it doesn't mean stop. It just means keep going until you have a definite answer. So no info doesn't mean anything to us. We just have to keep going until we find something that works. And what is going to
Mr. Brown,
Yes, sorry.
how did you get p equals 2, 3 for the last one? Because I'm just
Where am I looking at?
the question of 4.
P is equal to what?
2, 3, 2/3.
I just did properties of exponents. So this is n to the first 1 minus 5/3. 3/3 minus 5/3 is negative 2/3. So 2/3 in the denominator.
Mr. Brown,
Yes.
for the first one, could you have done the nth term test? And wouldn't it give you 2/5?
You could do the nth term test. Let me look.
And it wouldn't give you
Um,
0.
It wouldn't be 2/5. You would want to do L'Hopital's rule technically. But you are right. You could do the nth term test for that first one.
Okay.
Or actually, no, I'm lying to you. No, do L'Hopital's rule because it converges, so the nth term test wouldn't work.
How would we
If
know to
it's that
do
complicated.
L'Hopital's rule?
Yeah. Because you have to remember the nth term test can only prove it diverges. It can't prove that something converges.
But like, what would we know to use the L'Hopital's rule?
We'll get to one today that uses it.
Oh, well.
If you just hold tight. All right, so let's go ahead and look at the limit comparison test. So we're going to go back and do the limit comparison test for that last one. And I'm going to go ahead and just kind of go through like I did for the direct comparison test, like go through an example first, and then we'll kind of formalize it. So the limit comparison test, It will always work when the direct comparison test works for the most part. But it does also is nice, it will work when sometimes the direct comparison test doesn't. So I'm just gonna go through the steps of it and then I'll kind of formalize what we're doing because I think it's better just to kind of see someone work it out first. And so the limit comparison test starts off the same way. Like you're going to have a simple series to deal with. We can see what that simple series is related to. P would be equal to 2, which is greater than 1. So converges by the P-series test. And the limit comparison test is going to be a limit, but it's going to be a limit of the ratio of the simple series with the one you're trying to find. So there's going to be two ways you can set it up, and I'll kind of write it down. The formula you're trying is going to be the limit as n goes to infinity of either the simple one over the given, or the limit as n goes to infinity of the given one over the simple one. Order won't matter because of what we're looking for when we get to the limit comparison test. I'm going to go ahead and use just like that first formula. So setting it up, I have the limit as n goes to infinity. My simple one is 5n over n cubed. And then we have the complex one, which is the 5n plus 4 over the n cubed minus 4n. Not the prettiest limit to take, but we can simplify it, and these always in many ways simplify pretty nicely. So first off, we are dividing by a fraction. If I'm going to simplify that, dividing by a fraction is the same thing as multiplying by the reciprocal. So I can rewrite it like this. The limit as n goes to infinity, we have the numerator times the reciprocal of the denominator. And then here's a trick. You can go through and try to like factor things and cancel, or just kind of rearrange your factors. Since we have like a simple one and one related to it, order doesn't matter when you multiply. I'm going to go ahead and rewrite this integral as, not integral, excuse me, limit. So I'm going to keep the 5n, and I'm going to move the 5n plus 4 term underneath it, factor under it. And then I have the n cubed minus 4n, and I'm just going to shift the n cubed term underneath it. So you really are just multiplying two fractions. N is going to infinity. So if we're looking at these fractions, what is that first fraction going towards as n goes to infinity? 1. You have 5n over 5n, which is just going to give you 1, times we have an n cubed minus 4n over n cubed. What is that going to go to as n is going to infinity? Also 1. So what is the limit going towards overall? 1. Why is that important? And we'll formalize this on the next slide. For the limit comparison test to work, you want your limit to be finite and positive. So number 1, that is finite and positive. So basically, it can't be 0, it can't be D and E, and it's definitely not going to end up being something negative. Yes, please.
What if we get this limit of the simple one, which would be,
So if you lift your starting problem, is that what you're asking?
no, I'm saying like, looking at the original one.
Uh-huh.
I'm doing limits, we do what matters most, it's gonna be the exact same thing as the simple one, which would be 1 over 1, because they'd be the same.
I am showing you like this because I know where these problems are headed. So I'm going to recommend to go ahead and get rid of the denominator by multiplying by the reciprocal. And I'll also show you a way to shortcut this as well. But basically what we will conclude from this, if we do have something that is finite, then what we can conclude is that whatever the simple series does, the original one is going to be the same. So since the simple series converged, since one is finite and positive, we will have basically, so both series would also converge by, and this is the limit comparison test. So again, I know you like kind of shortcutting things you would have to show, you have to, of course, justify the simpler series. There's no way around it. What you can simplify, everything I have written in black or red is optional. So you don't have to clearly show like the simple over the given. As long as you think through and just know you're multiplying by a reciprocal and rearranging at the same time. So it is perfectly okay to jump straight to what I have in the blue. And then of course state the number you get and why it is important. And then of course your conclusion with the known test. So that's basically the limit comparison test. Again, I wouldn't jump always straight to the limit comparison test. I would probably do the direct comparison test first. Again, this is more the option like if the direct comparison one doesn't work, this will be like a second option of something to try. So let's formalize it. We have the limit comparison test. And then we'll just do one more example, and that's where I'm going to basically stop at today. For the limit comparison test, you are basically comparing a ratio of the limit. So it's going to be the limit as n goes to infinity of the given one over a simple one. Or you can flip it around. So you can also have like what we did in that previous example, the simple one over the given. Again, it won't matter because you just want your answer to be like finite and positive. And then two things can basically happen. The limit, again, could be finite and positive. That's what you want to happen. If that is true, then either both series diverge or both series converge. Well, what's the opposite for a limit of being finite and positive? The limit is DNE. So if your limit does not exist or 0, if you get a negative one, you probably just did the limit incorrectly. And then what do you think it's going to be if you get that as an answer? No info, your favorite. And you just get to keep trying, get another test to figure out something until you have a definite answer. Questions on the limit comparison test before I give you one last example with it today?
How do you know if it diverges or converges?
You would base off whatever the simpler series does. They would both do the same thing.
All right, yeah.
So like this one that we did, using the limit comparison test, I knew that the original series would converge because the simpler one converged as well. And I tried to find a fun one to do. So here's a fun one. Use the limit comparison test, so they are telling us which one to use, to determine whether this series converges or diverges, or if we can't determine the convergence by looking at the test. This is a weird series. This is a series defined by the sine of pi over the square root of n. If you're trying to like figure out what that series looks like, it's like the sine of pi, the sine of pi over root 2, the sine of pi over root 3, sine of pi over root 4. It's a weird series. And we want to figure out whether this series converges or diverges. Could try the nth term test, but the limit of this, let's think about it quickly. If n is going to infinity, pi over infinity is going to 0. This is a sine of 0, which is 0. We got no info. It's not a geometric one. It's not a p-series. Could do the direct comparison test. I will tell you the direct comparison test fails for this one, so we're not going to waste our time doing it, but it does fail for this one. The limit comparison test is the only one that we really have an option for, and this one is, honestly, the limit comparison test is the only one that would work for a series like this. What's tricky about this one, I think, is you have to always, when you're doing these tests, figure out a simpler series that is related to the one that you see. Any guesses of what the simpler series related to that one is going to be?
Pi over root n.
It is exactly pi over root n, which a lot of people feel weird about. I know when I first learned this topic, this was something that bothered me because you're thinking to yourself, well, this is like sine, which is like this oscillating function, right? And we're saying that somehow this is related to just the thing being plugged inside of it. Without going into like deep off tangent land mathematics of why we can do that, the simple version of why this works is if you just think about the graph of y is equal to sine of x. So instead of thinking about sine of pi over the square root of x, what does that graph look like? We know that graph looks something like this. When this series is starting off, like when we're closer to 0, that graph, even though it doesn't stay looking like that, this graph looks a lot like the graph of y is equal to x. Not forever, but just right around the origin, they look about the same. So in series land, removing the complexities of it, I know that looks terrible, but we're saying that the sine of x is approximately close to x around 0. Like clearly that falls apart very, very quickly. But that's kind of the gist of why we can do that. Some students also just like mess around, just tell me something to memorize, something to memorize. If you see a series with trig, the simpler series is often what's going to be plugged inside of it. So that's what we can kind of think. So let's go ahead and simplify this one. Let's justify it. That simpler series is what type of series? It's a p series. It's a constant with a n raised to a power. P would be 1/2, which is less than 1. So what do we know about that series? It diverges. And we're going to go ahead and do the limit comparison test. Again, it doesn't matter which one you put on top, because you just find the limit of the ratio. And a ratio is going to be a ratio. So I have the limit as n goes to infinity. I'm going to do the given one this time on top over the one that it is simpler to. So again, the goal, if the LCT is going to work, what do we want that limit to be? Finite and positive. I don't care what the number is, it just needs to be finite and positive. So let's go ahead and just take the limit. So n is going to infinity. So I have the sine of pi over the square root of n. What is just pi over the square root of n going to go to? 0. So like this denominator is going to 0, not looking good. Up here in the numerator, that's going to become the sine of 0. But what is the sine of 0 equal to? Also 0. Matthew Den, this is for you. We have 0 over 0. What do we need to do now? L'Hopital's rule. Are you ready? So let's review how we do that rule. Take the derivative of the numerator over the derivative of the denominator. I am going to rewrite it before I use that rule, so I have the limit as n goes to infinity. I'm going to think about this as the sine of pi n to the negative 1/2, just to make my derivative a little bit easier to find. We're not stressed out. We're confident in finding derivatives. So let's go ahead and do this. This is the limit. Again, I'm not dropping that limit until I actually take the limit. The derivative of sine is cosine. Leave the inside the same, times the derivative of the inside. So that negative 1/2 comes down in front. Pi is a coefficient, and that'll become n to the negative 3/2. All over the derivative of the denominator. Negative 1/2 comes down in front. Pi is a coefficient, n to the negative 3/2. Before I go to take the limit, what do I notice? Cancels. We're happy about that. So we really are just taking the limit of the cosine of pi over root n. So again, n is going to infinity. So what's pi over root n going to? 0. What's the cosine of 0? 1. Why is that 1 important? Is finite and positive. Since that is finite and positive, what conclusion can I make about that original series? Both series would diverge. So I could say either both series diverge, or I could say something like, so the original series diverges. How do we know? Because we did a limit comparison test. Now, if we had gotten something like 0 for D and E, then you would have to try a different test. And the next option going down the list would probably be something like the ratio test. But thankfully LCP worked for this one. Questions on that problem? All right, so let's go ahead and kind of see where we're at. Again, because these tests are going to start kind of piling up on us, especially next week. At this point, you should be able to do all of like homework 1 through 4. I'm hoping you haven't gotten behind already. This is again not the unit to get behind on. But we have the comparison test homework, which you can go ahead and start. When we come back from the long weekend, we just have 2 more tests to learn. We have the alternating series test, and then we have my favorite one, the ratio test, just because it uses a lot of factorials and they're just fun to simplify, and I'm a dork. But we just have 2 more tests to learn, and then your quiz basically is going to be on that Friday. So we are quickly kind of getting there. Again, I hope you feel like this isn't like difficult yet. It's just like a lot of stuff to know, and I think that's what makes it hard. Not necessarily that it's hard math, it's just a lot of math to know at once. But y'all can go ahead and get started on that homework with what time you have left in class.